want to talk about for AMP nervous system stuff here is just talking a little bit about how the action potential travels down the axon. We've talked about myelination, and we kind of talked about how it is going to influence how that action potential is carried, how it's going to speed it up and do that. So there's a couple different things actually that influence a neuron in terms of action potential speed. One of these is going to be the diameter of the axon. The larger the diameter, the faster the signal moves. It's kind of like a hallway. The bigger the hallway, more people can travel through it. The wider the crosswalk, more people that can cross it. The other thing is myelination. That's actually much more important. We're definitely going to see faster action potentials in these myelinated axons. So like we said, if an action potential is generated that axon hillock, it's going to travel all the way down to the synaptic knob, but we have two different ways that this can travel. In the unmyelinated axons, you're going to get what is called continuous conduction, where if we start talking about myelinated neurons, you're going to get what's called saltatory conduction. So continuous conduction, it's very similar to the analogies we've been using all along, which is when you trip that first domino, it knocks over the next one, knocks over the next one. So when you open one voltage-gated channel, it opens the membrane next to it, opens the membrane next to it. And if you had electrodes all along here, you would see this change all in every piece of membrane it would travel through. So anywhere you had that electrode, you would see the same depolarization, repolarization on it. That is continuous conduction. Saltatory or saltare means in Spanish to leap. So if you've ever seen Dora, when she wanted to jump, she'd be like, salta, salta, salta. It means it's going to jump. So what's going on here with those myelinated axons, you have 1 millimeter where there's unmyelinated regions. So each 1 millimeter, there's going to be those nodes of Ranvier. What we're going to see is that depolarization is going to jump from one of those to the next one, and we're only going to have voltage channels and the ability for it to depolarize at each one of those nodes. But we're going to get much more sensitive gates, and it's going to mean that this depolarization is going to kind of jump from node to node to node. So how it works on these ones, they're only at these nodes. There's a limited, the myelinated regions, there's hardly any voltage or other channels there. But they're well insulated, don't let ions get in or out. At those nodes, the nodes of Ranvier, you're going to have a large number of these voltage-gated channels that are extremely sensitive. And they're not going to have that myelin on them. So what's going to happen when you initiate an action potential, that diffusion of sodium is going to come in there through those myelinated regions. It's going to move through there relatively fast through those myelinated regions. And when you get any start of a weak sodium current there, that's enough to trigger that next voltage-gated channel. So they're much more sensitive to that depolarization. And because of that, what you're going to get is this jumping of depolarization from this node to the next node to the next node. So it's kind of like walking heel to toe versus running in terms of how you could talk about how this is jumping further up. So you can kind of see here with these myelinated regions, there's nothing going on here, but this depolarization, as it's a ways away right here, as it's moving across, this is going to cause this next one to trigger, which is going to send sodium in. It starts moving along here, and when it's still a ways away, it's going to cause this one to depolarize, and it's going to, again, that depolarization jumps from node to node to node. That is what saltatory conduction is. So again, faster speeds on these ones, and again, more efficient in that it doesn't require as much energy to repolarize all this membrane. You only have to repolarize in these nodes. It's the only spot that's depolarizing. So it's actually more efficient in terms of energy usage for those neurons. So myelinated axons, again, definitely going faster than that. And again, the wider diameter ones, that is also, so a wide diameter myelinated axon is going to be your fastest type of conduction. We're going to see that there is different types of nerve fibers. You have these different classes of nerve fibers that are either myelinated, wider, other stuff like that. So group A, these are the ones 150 meters a second. I mean, that's approaching about 280 miles an hour in terms of those speeds. So these are large diameter myelinated fibers. Most of your somatic motor neurons and sensory neurons would fall into this class. Very quick, good localization. We're able to see where this stuff is at really easy. Very quick signals, works well with coordination, everything else like that. Group B and C, these are either small in diameter or unmyelinated, or both. So a lot more of our visceral motor and visceral sensory. So group B going to be smaller in diameter. Unmyelinated, they travel much slower, about 10 times slower than the myelinated ones, so about 15 meters a second. And then the group C ones are quite slow at 1 meter a second, so those are probably small diameter and unmyelinated ones. Again, much slower. The other thing we can talk about is these neurons in terms of how they are kind of meshing together, how they're making some type of network. We're going to see that you can have what's going on here is called convergence. So like a lot of times with sensory, you're going to have multiple sensory receptors and neurons connected to those that are feeding into kind of like tributaries come together to make one main river. So multiple sensory neurons going to upstream cell and determining that. So, whoops, sorry about that. So what it means on these ones, these convergent circuits, this a lot of times happens with sensory. You have multiple inputs going into a single cell, and this might be, again, multiple ones at this next level going to one upstream. We see this a lot with sensory. Diverging circuits, we see this a lot more with motor output. On this one, you have one neuron that talks to multiple neurons, which talk to then multiple neurons, and very quickly. So if you had like one neuron in up here, it might be able to activate 15 motor neurons down here because it diverged out. Like I said, we see this a lot in skeletal muscle. You can have some of these ones that feed back on the cell, so these reverberating circuit type of neuron networks. Do these during breathing with sleep, so you have an output that is also feeding back up to the input to keep sending the signal back and around. There's also something called in parallel after discharge, which is multiple pathways to get to the same point. These are helpful in high order thinking. I, for some reason, have lost the image on here, but again, the main thing on these ones is it would be kind of multiple pathways getting to the same output neurons. So really, this is it for the nervous system. So after this one, we'll be working on senses, and that is our last area of really AMP1. So I'll see you next time.